Hello everyone, welcome to Bamane Pharm Lectures, where we make pharmacy simple. And in today's lecture we are going to talk about freezing point method as one of our third methods used to adjust solutions to isotonicity. In our previous videos we looked at gram-molecular method as one of the first methods used to adjust solutions to isotonicity. We also covered sodium chloride equivalent as one of the second methods used to adjust solutions to isotonicity. And today we are going to concentrate much about freezing point method as one of the third methods used to adjust solutions to isotonicity. And if you did not watch the first videos where we covered gram-molecular method and sodium chloride equivalent, I will advise you to go and check out for those videos so that you can also learn how to adjust solutions to isotonicity using gram-molecular and sodium chloride equivalent. And for those who don't know me, my name is Bamane and I am a tutor. So today pick up your pen and a calculator and be very attentive to learn about freezing point method. What is freezing point method? Freezing point method, sometimes we call it cryoscopic method. So those words sometimes can be used interchangeably. Don't get confused, they mean the same. As we discussed the previous methods, you understand that cryoscopic method or freezing point method is also a colligative property. And this colligative property is independent of the nature of substance being dissolved, but rather it depends on the number of units into which a substance breaks up when dissolved in a solution. So when we say that it is independent of the nature of substance being dissolved in a solution, but rather it depends on the number of units into which that substance breaks up when dissolved in water. We can take an example of sodium chloride. Sodium chloride is an electrolyte, and given it is an electrolyte, it means that when sodium chloride is dissolved in water, it is going to dissociate into sodium ions and chloride ions. So sodium chloride forms two ions, that's sodium ion and chloride ion. And this is what freezing point depression depends on, but it doesn't depend on the nature of substance. Let's say sodium chloride, let's say dextrose. Dextrose is the non-electrolyte. And whenever we talk about units, we mean ions for those substances that dissociate when dissolved in solution like sodium chloride. But when we talk about molecules, we simply mean those substances which do not dissociate when dissolved in solution. For example, dextrose. Dextrose is a non-electrolyte. So when dissolved in a solution, we don't expect it ionized. It instead remains as a molecule in that solution. But for substances which when dissolved in water ionizes partially, such substances contain a mixture of both ions and molecules. So put a key difference between those two terms. Therefore, the inclusion or presence of these ions in a solvent lowers the freezing point of that solvent. For example, we all know that water freezes at 0 degrees Celsius, and that is pure water. So what happens is, if we get any substance or solute, let's say sodium chloride or dextrose, and we dissolve it in water in a specific volume, let's say 100. That means that this solute, which may be sodium chloride or or dextrose is going to depress the freezing point of water to a certain temperature, and that is what we call the freezing point depression of a certain substance. In case other substances are dissolved, freezing point is depressed. For example, we all know that the temperature at which blood plasma and tears freezes is negative 0.52 degrees Celsius. Therefore, that means that any substance that freezes at negative 0.52 degrees Celsius is said to be isotonic with body fluids. And whenever we talk about body fluids, we simply mean tears and blood plasma in that case. That is why you realize that blood has got a variety of components, solids dissolved in it. So when blood is, for example, freezing, it will freeze at a freezing point of negative 0.52 because it contains dissolved ions. And everything that we are meant to administer or give by intravenous infusions, they should be isotonic with blood plasma, or they should freeze at the same point, at the same temperature as that of freezing, as that of freezing point of blood. Therefore, that means that whenever we are given solutions, it is our concern to know whether these solutions are isotonic before we can administer them to patients to avoid irritation and damage to cells. That means that we need to adjust such solutions to isotonicity in order to render them isotonic with blood plasma. And by doing that, we need to know how we can calculate for the percentage of adjusting substance required to make a solution isotonic. And that can be calculated from the formula W is equal to 0.52, which is the freezing point depression of body fluids or blood plasma, minus A divided by B, where A is simply the freezing point depression of an adjusted isotonic solution. For example, if they want you to if they have given you a solution of, let's say, propane hydrochloride, and they want you to make it isotonic with blood plasma. So the isotonic, the propane hydrochloride becomes the freezing point of propane hydrochloride becomes the freezing point depression of an adjusted isotonic solution in that case, as we shall look at when we reach other examples. B is the freezing point of a 1% solution of adjusting substance. Let's say if they want you to use sodium chloride as the adjusting substance in that case. So the freezing point depression of the 1% of sodium chloride will be the letter B, and that is the percentage of substance to be added. If it is sodium chloride, it will be that. If it is dextrose, then it will be our W in that case. So what does that mean? Some solutions contain more than one substance or solids. That means that when we are dealing with freezing point depression method, since it is dependent on the number of units being dissolved in that solution, that means that each unit exerts its own effect on freezing point depression, independent of the others. Meaning that every substance in that solution exerts its own effect on freezing point depression. So that means that if you have more than 1, 2 or 3, for example, each unit exerts its own effect on freezing point depression. That means that in that case, if we are dealing with more than one solute, A is simply a sum of the freezing point depression of all those substances being dissolved in that solution, as we shall look at it in our first example. Let us look at the first example. For example 1. A 1% solution of procaine hydrochloride freezes at negative 0.122 degrees Celsius. What concentration of sodium chloride should be added to render a solution isotonic? When you read this question, you realize that they want us to use sodium chloride as the adjusting substance. But we have procaine hydrochloride as our main substance in that solution. But we need to adjust this solution to isotonicity. The first thing always is to compare. If you have one ingredient, in that case, like for this question, where we have only procaine hydrochloride as the ingredient in the formula, that means we have a single substance. So we are going to compare the freezing point of procaine hydrochloride with that of blood plasma because it is the standard we have. So we shall say, since 0.122 degrees C is less than 0.52 degrees C, we are using 0.52 degrees C because this is the standard freezing point of blood plasma, and all these solutions are intended for administration into the body. They must be isotonic with body plasma. But we know that blood plasma freezes at this temperature. So any substance which freezes at this temperature, it is said to be isotonic with blood plasma. But when you look at 0.122 is far less than this. But we are saying that for that solution to be isotonic with blood plasma, it must have a freezing point depression of 0.52. So what does that mean? That means that when we get the difference between these two, we shall get a freezing point depression that is required for the adjusting substance. So that means freezing point depression required for adjusting substance, which in this case is dt prime 1, will be equal to the difference between the 0.52 degrees C, which is the standard freezing point depression, minus 0.122 degrees C. And when you subtract this, you get 0.398 degrees C. It means that when we get this freezing point depression and we add it onto this, we get this. Therefore, this remainder is what gives us the freezing point depression for the adjusting substance. So from this, we know that we already have the freezing point depression of the adjusting substance, which is in this case sodium chloride, and that is for the 1% solution. So from first principle, we are going to say that freezing point depression of 0.576 degrees C is produced by 1% solution of sodium chloride. How about the 0.398 degrees C? This will be produced by 1% divided by 0.576 times 0.398 degrees C. And when we compute this, we shall get 0.69% solution of sodium chloride. That means that we need 0.69% solution of sodium chloride to render this solution isotonic with blood plasma. But also for those who may wish to use the formula, we know that W is equal to 0.52 minus A divided by B. whereby 0.52 minus freezing point depression of an adjusted isotonic solution, which is the 0.122 divided by freezing point depression of the 1% solution of adjusting substance, which in this case is 0.576. And when you compute this, we shall still get 0.69% solution of sodium chloride. Therefore, that is how we attempt such a question. Let's look at our second example. Example 2. Find the concentration of sodium chloride required to render a 1% solution of cocaine hydrochloride isotonic with blood plasma. We say the first thing you compare, if you have one ingredient, like in this case we only have cocaine hydrochloride, we shall say since the freezing point depression of cocaine, which is 0.09 degrees C, is less than 0.52 degrees C, we shall get the difference between the two. And the remainder will be the freezing point depression required for the adjusting substance, which in this case we have sodium chloride as our adjusting substance. So we shall say freezing point depression required for adjusting substance, which in this case is sodium chloride, will be equal to 0.52 degrees C minus 0.09. And when we subtract this, we shall get 0.43 degrees C. So this is the freezing point depression required for our adjusting substance, which in this case, it is sodium chloride. So from our relationship, we know that the freezing point depression of a 1% solution of sodium chloride is 0.576 degrees C from our previous example. So we shall write that from first principle, where what we know is the freezing point depression and what we are looking for is the percentage strength of the adjusting substance. So we shall have that on the right hand side. So we shall say 0.576 degrees C is the freezing point produced by 1% solution of sodium chloride. How about our remainder, which is necessary for the adjusting substance, will be the freezing point depression will be produced by 1% divided by 0.576 times 0.43. When you compute this, we shall get 0.75% solution of sodium chloride. That means that we require 0.75% solution of sodium chloride in order to make this solution isotonic with blood plasma. You can as well go and calculate it from the formula where we say this is that minus A divided by B, whereby we know 0.52 minus 0.09 divided by the 0.576, and finally we shall have 0.75% as the percentage required for sodium chloride and just such a solution to isotonicity. Let's look at our third example, and where you don't understand, please drop your concern in the comment section. I will be happy to help you. Our third example. In our third example, feel free to pause this video and calculate it out and see whether you arrive at the same answer with me. In our third example, they are telling us to calculate the concentration of sodium chloride required to render a 1.5% solution of procaine hydrochloride isotonic with blood plasma. In this case, they have given us for a 1.5. But in reality, we only know the freezing point depression of a 1% solution. So the first thing we are going to do in this case is to convert to get the freezing point depression of a 1.5% solution of procaine hydrochloride, given that we already know the freezing point depression of a 1%. So from first principle, we are going to say that what we are looking for is the freezing point depression. What we know is the percentage strength of the solutions. So we shall say 1% solution of procaine hydrochloride produces a freezing point depression of 0.122 degrees C. How about the 1.5% solution of procaine hydrochloride will produce 0.122 divided by 1% times 0.15. And when we compute this, we shall get 0.183 degrees C. So this is the freezing point depression produced by a 1.5% solution of procaine hydrochloride. But this is not the answer. We need now to compare the freezing point depression of a 1% procaine hydrochloride with that of blood plasma. And when we compare the two, we realize that this freezing point is far less compared to that of the freezing point depression of blood plasma. Therefore, the remainder will be the freezing point depression of the adjusting substance, which in this case is still sodium chloride. So we shall say freezing point depression required by the adjusting substance which in this case it is sodium chloride. It will be 0.52 minus 0.183, and when you compute this, we shall get 0.337 degrees C. So this is the freezing point depression required for our adjusting substance, which in this case it is sodium chloride. So after obtaining the freezing point depression of sodium chloride, our main aim, we need to know this freezing point depression produces which percentage. But already we know that the freezing point depression of the 1% sodium chloride is 0.576 degrees C. So we shall begin with this and say that if 0.576 degrees C is the freezing point depression produced by a 1% solution of sodium chloride, how about the remainder, which gives us our adjusting substance? So the 0.337 degrees C will be produced by 1% out of the freezing point depression of sodium chloride times 0.337. And when we compute this, we shall get 0.59%. That means that we need 0.59% solution of sodium chloride to render this solution isotonic. That means if you write your final product formula, we shall have procaine hydrochloride as 1.5 grams. We shall have sodium chloride as 0.59 grams, and then water, distilled water or water for injection, add to 100. That will be our final product formula in this case. I hope you got the same answer with me. Let's look at our fourth example. Our fourth example. Calculate the concentration of sodium chloride that should be added to water to produce an isotonic solution. When you look at our fourth example, it is a bit different from what we have been solving. So in this case, we have only been given sodium chloride, and that is the adjusting substance at the same time. So that means here we are simply going to compare the freezing point depression of blood plasma and that of 1% solution of sodium chloride. But remember, we are looking for the concentration, and every time they talk about concentration, we mean concentration in percentage weight in volume. So in this case, we shall start from first principle because they have already provided to us the freezing point depression of the 1% solution of sodium chloride. So what we are looking for is the percentage strength. So we shall say 0.576 degrees C is the freezing point depression produced by the 1% solution of sodium chloride. How about the 0.52 degrees C? Because this is the freezing point depression of blood, it will produce 1% divided by the freezing point depression of our adjusting substance, which in this case is sodium chloride, times 0.52 degrees C. And when we compute this, we shall get 0.9% solution of sodium chloride. That explains why normal saline is said to be isotonic with blood plasma. And this is how we can solve such a question. Our fifth example. Our fifth example will now be your assignment. Feel free to pick up your pen and the calculator and solve it out. And the answer you get, drop it in the comment section. I'll be happy to tell you whether you got it right and help you understand it better. And if you find this video very useful, please subscribe to my channel, share it with your friends and other classmates who may also find it very useful. Like it, share it everywhere, help everyone out there understand injection is very well. And where you don't understand, please drop your concern in the comment section. I'll be right there to help you. And in case you have any topic you want us to cover next, you can still drop it in the comment section. I'll be reviewing them and see how I can help you understand pharmacy calculation is better. See you in the next lecture, and don't forget, this is just part 1 of freezing point method. We are going to look also at part 2, where we shall be looking at complex questions on tiny 2 or more substances, and we need to adjust them to isotonicity, still using freezing point method. Let's catch up in the next lecture. And please don't forget to click the notification button to keep you updated with more simplified pharmacy lectures. Let's catch up in the next lecture.